Welcome to the explainer. Okay, let's dive into this. Have you ever just looked around your house, or maybe even at the food on your plate, and thought about the invisible chemistry holding it all together? Or actually, what's even more interesting, how we take it all apart. Today, we're exploring the absolutely fascinating hidden science of chemical separation that's constantly at work in our everyday lives. We're going on a journey from ancient traditions to life-saving modern medicine. I mean, really, think about this for a second. How exactly do we get pure, sweet, white crystals of sugar out of a tall, raw green sugarcane plant? Or on a much more critical level, how do doctors isolate a specific disease, like malaria, from just a few drops of really complex human blood? We are constantly extracting the pure from the raw. And to understand how we pull off these everyday miracles, well, we first have to understand the nature of what we're pulling apart. Section 1, classifying what we mix, the invisible world. Before we can even think about separating a mixture, we have to look closely at how things combine in the first place. Fundamentally, mixtures fall into two distinct behavioral categories based on how uniform they are. And this brilliantly illustrates the core difference. Think about a homogeneous mixture, or a true solution, like sugar dissolved in water. The composition is completely uniform throughout the whole thing. Your first sip is just as sweet as your last. But contrast that with a heterogeneous mixture, like sand mixed into water. It's totally non-uniform. You can easily see the individual sand particles, and if you just wait a bit, they'll physically settle right down at the bottom. To really prove just how uniform a homogeneous mixture is, we can do a fun little trick with light. When we shine a laser pointer through a beaker of salt and water, which is a true solution, the light passes straight through to the other side. Because the mixture is perfectly uniform, those dissolved salt particles are simply too small to interfere with the laser beam. It stays completely invisible inside the liquid. But watch what happens when we switch things up. If we mix chalk powder into water, we get a heterogeneous mixture. The particles here are much larger, and they just sort of hang out, suspended in the liquid. As the laser passes through, these larger chalk particles actually scatter the light, suddenly making the entire path of the laser beam visible right through the water. Now, check out a mixture of just a few drops of milk and water. I have a quick question for you. Why does this milk mixture scatter the light so strongly, creating that distinct glowing line? Well, it's because, much like the chalk, milk does not form a true uniform solution in water. The suspended fat and protein particles are large enough to literally bounce the light around. So simply by shining a light, we can visibly identify the physical nature of the mixture we're dealing with. Section 2. The power of concentration. When math saves lives. Now that we know what is mixing, let's shift our focus to how much is mixing. We define concentration as the exact amount of solute, the stuff being dissolved, in a given amount of solvent, which is the stuff doing the dissolving. A perfect real-world example of this is the oral rehydration solution, or ORS. Formulated by the Indian pediatrician Dr. Dilip Mahalanobis, ORS requires highly specific amounts of salt and sugar in a fixed amount of water to properly treat dehydration. If you just throw random handfuls of salt and sugar into a glass, you don't get ORS. You just get salty sugar water. That exact concentration is what revolutionized rehydration therapy and literally saved millions of lives globally. So the crucial point is that we absolutely must have accurate ways to measure and communicate these concentrations. Depending on what exactly we're mixing, we use different mathematical formulas. If we're mixing dry powders into foods, we use a mass by mass percentage. If we're dissolving a solid medicine into a liquid, we use mass by volume. And say if a farmer is mixing a liquid pesticide into a water sprayer for their crops, they use a volume by volume percentage. You actually interact with these formulas every single day, right in your own pantry. Just grab a nutritional label for some milk powder. This relies perfectly on the mass by mass percentage. It tells you exactly how many grams of a solid solute, like say 49 grams of sugar or 26 grams of fat, are present in 100 grams of the total powder mixture. And in a hospital setting, reading these concentrations correctly is literally a matter of life and death. Take a 500 milliliter glucose intravenous infusion bottle. You'll see it labeled 5% weight by volume, or mass by volume. This tells the doctor that there are exactly 5 grams of glucose dissolved in every 100 milliliters of the liquid. It's just a simple math equation, but it ensures the patient receives the exact right amount of nutrients directly into their bloodstream. Section 3. The magic of crystallization. Extracting the pure. Okay, now that we totally understand solutions and concentrations, how do we reverse the whole process? How do we extract a pure solid out of a liquid mixture? Well, the secret key here is temperature. Every solvent, like water, has a maximum capacity for how much solute it can hold. We call this its solubility. But here's the catch. This capacity changes with heat. For solid solutes, as the temperature goes up, the liquid can hold more and more of the solid. Conversely, if you're dissolving a gas into a liquid, the solubility actually goes down as it gets hotter. By manipulating this simple temperature rule, we can literally force solids to separate from liquids. Let's walk through this brilliant lab procedure for crystallization. First, you take a substance, like copper sulfate, and heat it up in water, dissolving as much as you possibly can until the solution is completely saturated. Next, you filter that hot mixture just to get rid of any undissolved impurities. And finally, you just let the solution cool down slowly. Because the cooler water simply cannot hold as much of the solid as the hot water did, the pure solid is forced right out of the solution, assembling itself into these beautifully regular geometric patterns that we know as crystals. And crystallization isn't just some modern laboratory trick. It is an ancient practice and a massive force of nature. In the coastal areas of India, local communities historically used this exact science to harvest punga salt by boiling concentrated sea brines, or karkach salt by relying on the slow, natural evaporation of seawater. Nature does this too, over thousands and thousands of years, creating massive, breathtaking crystal deposits, like the natural quartz formations you can find deep inside the Masmai Cave in Meghalaya.
Section 4. Capturing the Uncatchable. The Art of Distillation.
So we've talked about separating solids from liquids, but what if you accidentally mix two liquids together, say acetone and water? They are completely miscible, meaning they totally dissolve into one another. How on earth do you pull two liquids apart? Let's move to our next technique and see how this builds on everything we've learned so far. Distillation exploits boiling points. If two liquids have a boiling point difference of at least 25 degrees Celsius, we can just heat the mixture up. The liquid with the lower boiling point is going to vaporize into a gas first. We capture that vapor, run it through a cooled condenser tube to turn it back into a liquid, and then collect it in a separate flask as a pure distillate. The other liquid is left completely behind. Now, what's really interesting about this slide is how this exact distillation chemistry is used for art and culture. In the town of Kannauj in Uttar Pradesh, which is the perfume capital of India, they use an ancient distillation setup known as the Deg Bapka method. They literally distill the scent of the earth. By processing clay and capturing the aromatic vapors, they bottle the beautiful, earthy smell that rises from the ground after the very first rain. It's a natural perfume called Mitti Ka Itar. It's basically rain, captured in a bottle. From life-saving medical drips in an ER to capturing the poetic scent of the rain, the science of mixtures and separation is absolutely everywhere. So as we wrap up this explainer, I want to leave you with this thought. Look at the cup of tea or coffee on your desk right now, or look at the product sitting in your pantry. What invisible mixtures, precise concentrations, and hidden chemical miracles are you interacting with right now without even realizing it? Keep wondering, keep exploring, and we'll see you next time.